Hey guys, tonight we begin with a question that reaches deep into the very bones of our planet. What if we are not the first civilization on Earth? For as long as we've studied history, we've believed ourselves to be the pinnacle, the first species to build machines, split the atom, and transform the planet with technology. But buried beneath millions of years of stone and sediment, there are strange clues. Whispers from epochs so ancient, they stretch far beyond the reach of human memory. Clues that suggest the impossible, that perhaps another civilization once thrived here, long before us. This idea is known as the Silurian Hypothesis. It asks, if an industrial civilization existed millions of years ago, what traces would remain? Could we even detect it? Or would time, erosion, and the slow churning of Earth's crust erase every footprint they ever left behind? Before we settle in and begin our peaceful journey, take a moment to like this video and subscribe, only if what I share here truly resonates with you. Your support helps me create more of these calming stories, and if you feel like it, let me know where you're tuning in from and what time it is. It's always fascinating to see the many corners of the world where we connect. Now, dim the lights, make yourself comfortable, and let's ease into tonight's journey together as we explore the mysteries of the Silurian Hypothesis and the haunting possibility that we are not the first. Chapter 1: The Silence of Deep Time. Imagine standing on the edge of a vast canyon. Before you, layer upon layer of coloured stone stretches into the distance. Reds, browns, pale yellows and deep blacks, each one a page in Earth's diary, written not with words, but with minerals, fossils and chemical traces. Geologists call this the stratigraphic record. To them, every band of stone tells a story, of oceans that once covered the land, of forests that rose and fell, of climates that warmed and froze again. But here's the challenge. This record is far from complete. The deeper we go, the further back in time we travel. Yet with each mile downward, the story becomes harder to read. Rock shifts, melts, and erases itself under the slow but relentless movements of plate tectonics. Oceans open and close. Continents collide, entire mountain ranges are lifted into the sky, only to be worn down into dust. In this grand cycle, even the traces of vast civilizations, if they ever existed, could be scattered like ashes in the wind. To give perspective, modern human industrial civilization, our cities, our highways, our plastic waste, has only existed for about 300 years. Out of the 4.5 billion years of Earth's history. That is less than a blink in geological time. If humanity were to vanish tomorrow, within just a few 100,000 years, most of our buildings and structures would collapse. Forests would reclaim our cities. Even the tallest skyscrapers would crumble into heaps of rust and dust. In 10 million years, it is likely that almost nothing recognizable would remain on the surface, and yet, something would remain. Geologists studying our time call it the Anthropocene fingerprint. It's not the buildings themselves that endure, but the subtle signals we've left behind. Layers of plastics that never truly decompose, but break into tiny fragments. Radioactive isotopes from nuclear testing spread across the globe. Sharp changes in atmospheric carbon dioxide recorded in ice and stone. These are signals strong enough to last millions of years. To a civilization of the distant future, these chemical fingerprints might be the only proof we ever existed. Now imagine turning this around. If another civilization had flourished tens or even hundreds of millions of years ago, what signs would they have left for us? Would we see unusual layers of metals like copper or aluminum where they should not exist? Would we find isotopes that suggest nuclear reactions far older than humanity? Would we notice sudden shifts in the atmosphere, unexplained by natural causes. The sobering truth is that Earth has already gone through dramatic events that mirror what our industrial age is causing today. Massive spikes of carbon dioxide, sudden extinctions of countless species, abrupt climate swings. Some of these changes are blamed on natural causes like volcanic eruptions or asteroid impacts. But the patterns to some scientists raise an unsettling question. What if some of these events were not natural at all? The Silurian Hypothesis takes root in this silence of deep time. It doesn't claim that there was a civilization before us. It simply asks, could we ever know if there had been? And if the traces were buried deep beneath oceans or recycled back into magma, what would remain to tell their story? To understand this question, we must first explore how Earth's layers preserve or erase the marks of history. Because if civilizations have come and gone before us, their footprints would not be in ruins or artifacts, but in chemistry, in stone, and in the faintest whispers of the fossil record. Chapter 2. The Memory of Stone. How Earth Preserves and Erases Civilizations. When we think of memory, we often imagine something delicate, our minds holding images of childhood, or a book storing words across its pages. But Earth has its own kind of memory, written not in paper or ink, but in stone. The ground beneath our feet is like a library, filled with records of ancient seas, lost forests, and vanished worlds. Yet unlike a carefully kept archive, Earth is a restless keeper of history. It forgets almost as much as it remembers. To see how this works, let's imagine a single grain of sand. Perhaps it began as part of a mountain, carved slowly by rain and ice. Over thousands of years it broke free, carried down rivers, tumbled into the ocean. Eventually it joined countless others, settling on the seafloor in a layer of sediment. With time, more layers buried it deeper, pressing it into stone. That stone becomes a chapter in the Earth's diary, preserving tiny fossils, chemical signatures, even traces of ancient atmospheres trapped in bubbles. But here is the catch. Not all layers survive. Over millions of years, tectonic plates grind against one another, pushing some layers deep into the mantle where they melt and are lost forever. Others are lifted high into mountain ranges, where wind and rain wear them away. What survives is fragmented, a patchwork quilt of memory, filled with gaps where entire ages may have been erased. This is why the fossil record feels like reading a story with missing pages. For example, the earliest known fossils of complex animals suddenly appear about 540 million years ago, during what scientists call the Cambrian explosion. To us, it looks like life burst into existence almost overnight, but many researchers believe the record is incomplete. Entire stages of evolution may have been lost to erosion, leaving only fragments of what truly happened. Now let's bring this back to the Silurian Hypothesis. If a civilization had arisen tens or hundreds of millions of years ago, its ruins, their cities, their machines would almost certainly be gone. Wind, water, and tectonics would erase them in a fraction of geological time. What would remain are the subtle traces locked inside rock, unusual chemical fingerprints, odd concentrations of metals or isotopes that cannot be explained by natural processes. Think of it this way. When we look back at the Earth's story, we don't see the details of ancient forests, but we can find the carbon they left behind in coal. We don't see the bones of every dinosaur, but we see the iridium-rich layer left by the asteroid that ended their reign. In the same way, if there were ancient industrial civilizations, we wouldn't expect to find skyscrapers or roads, but perhaps we might find a layer of plastic-like residues or traces of synthetic chemicals unknown to nature. To understand this better, scientists often compare our present moment, the Anthropocene, to past geological epochs. What fingerprints are we leaving behind that might be detected millions of years from now? For example, 1. Plastics. These long-lasting polymers are breaking into microplastics now found everywhere, from the depths of the ocean to the ice of Antarctica. Over time, these fragments could sink into sediments, becoming a permanent marker of our age, a strange layer of synthetic materials, unlike anything that came before. 2. Fossil fuel. Burning. By burning coal, oil and gas, we've pumped enormous amounts of carbon dioxide into the atmosphere. This carbon has a distinct isotopic signature, lighter than naturally occurring carbon, which means future geologists could recognise a sudden, unnatural shift in the balance of the atmosphere. 3. Radioactive isotopes. Nuclear testing in the 20th century released rare isotopes such as plutonium-244 into the environment. These do not occur naturally on Earth in measurable amounts. If detected millions of years in the future, they would be a clear signal of technological activity. If this is the kind of evidence we will leave behind, then similar signatures might exist from civilizations before us. But here we face the problem of time. Even strong markers can fade. Radioactive isotopes decay. Plastics eventually break down under heat and pressure. Tectonic activity buries or recycles rock. Let's imagine an ancient civilization that flourished 100 million years ago. That is 10 times longer than humans have existed. In that time, continents have shifted dramatically. Oceans have opened and closed. Mountains we see today didn't even exist yet. Almost every trace of their world, if it ever was, would now be buried or destroyed. And yet, some mysteries linger in the record. For instance, scientists studying the Paleocene-Eocene thermal maximum about 56 million years ago found evidence of a sudden global warming event. Temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. Carbon isotopes in sediments reveal a massive release of greenhouse gases on a scale similar to what we're causing today. But the source is unclear. Was it volcanic activity? Methane hydrates released from the ocean floor? Or could it have been something else, something we haven't considered? This is the shadowy space where the Silurian Hypothesis resides, not as a claim, but as a possibility. It asks us to look at these strange events and wonder, are we really certain they are natural? Or could they be echoes of civilizations long forgotten? The Earth's memory is both fragile and enduring. Fragile, because entire histories can be erased. Enduring, because the tiniest chemical traces can survive for millions of years, whispering from the rocks if we know how to listen. And so, the search for past civilizations is not about looking for ruins, it is about learning to read the hidden language of stone. As we move forward, we will explore these geological puzzles more deeply. We'll look at great extinction events, strange anomalies in Earth's chemistry, and the question of whether some of them could be the fingerprints of forgotten civilizations. Chapter 3. The Erased Civilizations of Earth. Mass extinctions are like punctuation marks in Earth's story. Long flowing chapters of life are suddenly interrupted by abrupt endings, moments when most living things vanish, leaving only fragments of what came before. These are not gentle transitions, but dramatic upheavals, reshaping the planet in ways that would be impossible to imagine if we did not see the evidence preserved in stone. There have been 5 great extinction events that scientists recognize in Earth's history, often called the Big Five. Each one reset the course of evolution, wiping out dominant life forms and making space for new ones. But what if these violent chapters also erased more than just species? What if, hidden within those catastrophic losses, entire civilizations rose and fell, their traces swept away in the chaos? Let's explore this possibility gently, step by step. The Permian extinction. The Great Dying. About 252 million years ago, Earth experienced its deadliest known extinction. Around 90 to 95% of marine life and 70% of land species disappeared. Fossil records show entire ecosystems collapsing. The causes remain debated. Some scientists point to massive volcanic eruptions in Siberia, releasing enough carbon dioxide to trigger runaway climate change. Others suggest methane gas released from the seafloor could have amplified the warming. But imagine for a moment, if there had been a civilization before or during this time, the sheer scale of destruction would have been enough to wipe nearly all trace of it from existence. Even our own fingerprints, plastics, radioactive isotopes, altered soils would be shredded, scattered, or buried under volcanic layers. To future eyes it might look exactly as it does to us now, a natural disaster with no sign of technology. The Cretaceous extinction, the end of the dinosaurs. 66 million years ago, a massive asteroid struck Earth near what is now the Yucatan Peninsula. The impact released energy equal to billions of atomic bombs, setting forests on fire, sending tsunamis across oceans, and throwing enough dust into the atmosphere to darken the skies for years. Dinosaurs, except for the ancestors of birds, perished. This event is well documented thanks to a thin layer of rock enriched in iridium, a rare metal more common in asteroids than Earth's crust. That layer forms a clear global marker, like a line drawn in stone. Now here's an interesting thought. If an industrial civilization had existed just before this event, the asteroid would have obliterated it entirely. Cities would have vaporized, technology would have been pulverized, and the iridium layer would bury the evidence beneath itself like a blanket. Millions of years later, all we would see is the chemical scar of the asteroid, not the vanished civilization it might have buried. The Paleocene-Eocene thermal maximum. We touched on this earlier. An abrupt global warming about 56 million years ago. Carbon dioxide surged, oceans acidified, temperatures spiked, and ecosystems collapsed. The cause remains uncertain. Natural explanations exist, of course. Volcanoes, methane releases, but the scale is eerily similar to our own modern climate disruption. Could this have been the fingerprint of an earlier industrial age, one that rose and fell long before humans? It is impossible to say with certainty. But what is striking is how closely it mirrors the Anthropocene. Rapid warming, mass extinctions and chemical shifts in the atmosphere. If another species had industrialized, this is exactly the kind of signal they might have left behind. How extinctions hide civilizations. This is where the Silurian Hypothesis gains its weight. Extinction events act like cleaners of the geological record. They destroy evidence on a planetary scale, burning forests, flooding continents, and burying landscapes under ash, mud, and lava. Whatever came before is overwritten by the violence of nature. It is like trying to read a manuscript where entire chapters have been scorched away. You see the transition, the change in species, the sudden chemical signatures, but you cannot see what was lost. In that silence, there is room for speculation. To bring this into perspective, consider our own world. If humanity were to vanish tomorrow, what would remain after a catastrophic asteroid strike or supervolcano eruption? Perhaps only the faintest chemical traces, a spike in carbon dioxide, a scattering of synthetic molecules, maybe a few odd isotopes buried in sediments. Future species might wonder, was this purely natural, or was something else at work here? Let's imagine an ancient species, one we will never find bones or tools for. Suppose they thrived in the lush forests of the Carboniferous period, more than 300 million years ago, when oxygen levels were higher and insects grew to enormous sizes. Imagine they developed industry, harnessed energy, built cities along shallow inland seas. Perhaps their machines left behind chemical markers in the air and soil. And then, perhaps, they vanished in the Permian extinction. Volcanoes erupted, seas turned toxic, and 95% of life disappeared. Their cities collapsed, swept away by rising waters and buried beneath lava flows. The fossil record would remember almost nothing. To us it would look like a natural disaster, full stop. Yet in truth something more may have been lost, an entire age of intelligence, erased by fire and stone. This is what makes the Silurian Hypothesis so haunting. Earth's story is not continuous. It has gaps, sometimes millions of years long. We assume nothing happened in those gaps, because we have no evidence otherwise. But perhaps that is only because the evidence is gone, swallowed by extinction and erosion. Each extinction is both an ending and a beginning. It closes the book on one era, but it may also close the book on things we never knew existed. When life recovers, as it always does, it begins a new chapter on top of the ashes of the old. And with each new chapter, the earlier words fade further into silence. So when we ask, are we the first civilization? The truth may be unknowable, because if others existed, they may have been lost not just to time, but to extinction's fire, buried forever in Earth's shifting crust. As we move forward, we'll look at the fingerprints left behind by our own civilization, chemical, biological, and geological, and compare them to strange anomalies in Earth's past. Could those anomalies be evidence of civilizations we never knew? Chapter 4. The Anthropocene as a Fingerprint of Civilization. When future geologists, perhaps millions of years from now, dig through the layers of rock that represent our time, what will they find? This is not just a question of curiosity, but the foundation of how we imagine other civilizations that might have come before us. To ask whether an earlier industrial species once existed on Earth, we must first understand the traces we ourselves are leaving behind. Our own civilization becomes the case study, the fingerprint against which all others are compared. The Anthropocene, the age in which human influence dominates the planet, is marked not by towering monuments or fragile buildings, but by deep and subtle changes to Earth's systems. Our cities may crumble within centuries, and our roads may be erased by shifting landscapes, but the chemistry of our activities is being written into the planet itself. It is this chemistry, more than anything else, that will endure long after we're gone. Take carbon, for instance. By burning fossil fuels, we've released enormous quantities of carbon dioxide into the atmosphere. This carbon is not the same as the natural background carbon that cycles between air, ocean, and soil. Fossil fuels come from plants and animals that died millions of years ago, and the carbon they contain has a lighter isotopic signature. When we burn them, we release this distinctive carbon into the atmosphere, creating a chemical marker that settles into sediments and ice. Even millions of years from now, layers of rock will show a sudden, sharp shift in carbon isotopes, a sign that something unusual happened during our age. Plastics are another marker. These synthetic materials did not exist before humanity. They are found now in every corner of the Earth, in the deepest trenches of the ocean, in Arctic snow, even inside the bodies of animals. Over time, plastics break down into smaller and smaller fragments, but they do not truly vanish. Instead, they become part of the sedimentary record. Future geologists may find strange layers of a rock filled with plastic particles, a clear and unmistakable signal of an industrial society. Radioactive isotopes offer another fingerprint. The nuclear age left behind materials that do not occur naturally in measurable amounts. These isotopes, like plutonium-244, are embedded into soils and waters across the planet. Their half-lives stretch across thousands or millions of years, ensuring that long after cities fall, the radioactive signature of humanity will remain locked in the earth. Beyond these specific signals, there are broader patterns of change. Our use of fertilizers has altered the nitrogen cycle, leaving behind unusual concentrations of nitrogen compounds in soils. Mining and industry have redistributed rare metals like aluminum and copper, embedding them in places they would not normally be found. Even the sheer movement of Earth, our quarries, our landfills, our reshaping of rivers and coastlines, has created geological disturbances on a global scale. These changes may blur over time, but many will remain visible to anyone who knows how to read the language of rocks. Now let us imagine how this record might look to distant scientists in some far-off future. They dig into a cliff face and see a sharp boundary where the rock layers change suddenly. Below, the record is stable, with gradual shifts in climate and life. Above there is chaos, carbon levels spike, fossils of countless species vanish, and strange chemical markers appear all at once. To them, it might look as though Earth went through a sudden crisis, perhaps triggered by natural forces, perhaps by something more. They might never know for certain what caused it, just as we puzzle over the causes of past extinctions. This perspective is both humbling and haunting. It reminds us that our civilization is but one chapter in Earth's vast story. Even the most advanced technology, even the greatest cities we have built, may one day vanish without a trace, leaving behind only chemical whispers in stone. And it shows us why the Silurian Hypothesis is worth considering. If our own civilization can be reduced to such faint traces, then others before us might have vanished in the same way, leaving behind anomalies that we cannot easily explain. By studying our own impact, we create a mirror through which to search for others. The Anthropocene becomes not just the mark of our presence, but the template for imagining the evidence of civilizations we will never meet. And in this reflection, the possibility arises that we are not unique. Perhaps Earth has hosted others before us, their stories buried in layers of stone, their fingerprints hidden among the great shifts of climate and extinction. Chapter 5: Anomalies Buried in Time. As we peer into the vast expanse of geological history, we begin to notice moments that do not fit neatly into the natural rhythm of Earth's story. Tiny irregularities in rock layers, sudden chemical shifts, and unexplained concentrations of metals. These anomalies act like faint whispers from a past we cannot fully see. They hint at events that, if interpreted differently, might point to something extraordinary. Signs of activity unlike any natural process, perhaps even traces of civilizations lost to time. One of the most compelling examples comes from the distribution of rare metals and isotopes across ancient sediments. Scientists have discovered microscopic spheres of metal such as platinum, chromium, and even unusual isotopes scattered across rock layers that are tens of millions of years old. These metals appear in concentrations and patterns that mimic what modern geologists would expect from nuclear activity. Yet these deposits predate humans by an impossible margin. They are not the product of asteroid impacts or volcanic eruptions, at least not entirely, leaving a puzzle that challenges our understanding of Earth's past. Similarly, chemical spikes in carbon, sulfur and nitrogen are preserved in the rock record. Some of these shifts coincide with mass extinction events, where life seemed to disappear almost overnight. Traditionally, scientists have attributed these changes to natural causes, volcanic eruptions, methane releases, or asteroid impacts. But when we examine the magnitude and speed of some of these chemical alterations, they appear startlingly familiar. They resemble the fingerprints of industrial activity, the sudden release of greenhouse gases, large-scale mining, or even combustion on a planetary scale. These events raise an unsettling question. Could some of the anomalies in the geological record be the echoes of civilizations that existed long before humans? Another area of intrigue lies in the gaps themselves, the moments when the fossil record is silent. For millions of years, Earth seems to hold no sign of complex life, or entire ecosystems appear to vanish without explanation. These silent intervals are often dismissed as imperfections in preservation, yet they could also mask something far more extraordinary. If a civilization had arisen during such a period, the geological processes of erosion, sedimentation, and plate tectonics could have erased almost all visible traces. Cities, roads, and machines might have been destroyed or buried so deeply that the fossil record never captured them. Only subtle chemical or isotopic anomalies would remain, like whispers from a civilization that has been almost entirely forgotten. Even the fossil record itself can contain hints. Occasionally we find fossils with unexpected traits, unusual densities, or chemical alterations that do not fit the evolutionary patterns of the time. Some are dismissed as oddities or misinterpretations, but within the framework of the Silurian Hypothesis, they take on new significance. Could these irregularities reflect environments altered by intelligence? Could some organisms have adapted to chemical or physical conditions influenced by industrial activity millions of years ago? The questions are speculative, yes, but they are also grounded in the science of Earth's layered history and the ways in which chemical traces persist over immense timescales. In addition, ancient climate anomalies mirror modern industrial impacts in intriguing ways. Rapid warming events, sudden ocean acidifications, and abrupt carbon shifts are visible in the record. The speed of these changes, their global reach, and their chemical signatures often challenge natural explanations. While volcanoes and asteroid impacts provide plausible causes in some cases, the scale and precision of these events occasionally suggest something more directed, something unusual for a purely natural system. They are the kind of phenomena that, if observed in our own time, would be unmistakably linked to intelligent activity. Yet in the past they stand as mysterious events without clear origin. As we trace these anomalies through time, a pattern emerges. Earth's record is not a continuous smooth history. It is punctuated by sudden, often inexplicable events. Some of these are undoubtedly natural. Others may hold clues that are more extraordinary, waiting to be interpreted in a framework that includes the possibility of intelligence beyond our own. The challenge is that, unlike the evidence we leave today, these anomalies are fragmented, faint, and scattered across millions of years and countless layers of rock. They require patience, imagination, and a willingness to read Earth's story not just as it's told, but as it might be remembered after the passage of unimaginable time. And so, the anomalies buried in time invite us into a quiet, reflective journey. They encourage us to look at Earth not only as a witness to natural processes, but as a canvas that may preserve, in subtle and hidden ways, the echoes of beings we will never meet. Whether these traces point to other civilizations or to extraordinary natural events, they remind us of the fragility of existence and the impermanence of even the most advanced achievements. The story of Earth is vast, layered, and often silent, leaving us to wonder what might have occurred in those quiet chapters we can barely perceive. Chapter 6. The Challenges of Finding Ancient Civilizations. When we ask whether Earth has hosted advanced civilizations before humans, we immediately encounter a profound challenge. The planet is both generous and unforgiving in how it preserves history. Some traces endure for millions of years, while others vanish almost entirely. Detecting a civilization that existed tens or hundreds of millions of years ago is a task unlike any other, requiring imagination, patience, and a careful reading of subtle clues hidden in the geological record. The first difficulty is time itself. Geological processes move at a pace so slow that human intuition struggles to grasp it. Sediments accumulate gradually, layers are compressed into rock, and mountains rise and erode over millions of years. Plate tectonics, which shapes continents and ocean floors, can recycle rock into the mantle, where it melts and disappears entirely. Erosion wears away coastlines, rivers carve valleys, and glaciers grind entire landscapes into powder. These processes mean that the kind of evidence we might expect, buildings, roads, or machines, would be completely destroyed, leaving behind only indirect traces that require careful interpretation. Another challenge is the subtlety of the signals. Unlike natural events such as volcanic eruptions or asteroid impacts, which leave unmistakable layers of ash or iridium, the markers of a civilization are likely to be diffuse and scattered. Tiny isotopic shifts in carbon or nitrogen, small deposits of rare metals, microplastics, or synthetic compounds that persist in sediments, all of these could survive as faint whispers of industrial activity. Detecting them requires sophisticated chemical analysis, deep drilling into ancient rock layers, and careful differentiation from natural processes that can produce similar results. One of the questions scientists ask is whether an industrial civilization could even exist for long enough to leave a detectable trace. Our own species has had only a few hundred years of technological industry, a mere blink compared to the hundreds of millions of years complex life has existed on land. Even if a previous civilization arose, its period of technological prominence may have been brief, reducing the likelihood that evidence would survive the relentless grinding of time. In this sense, the very brevity of civilization works against its detection. Scientists also consider what markers would be most reliable. Chemical anomalies, especially in isotopes, are promising because they can persist over geological timescales. Artificial metals or alloys that do not occur naturally could leave lasting signals if concentrated enough. Fossil fuels burned by an industrial civilization could alter carbon isotope ratios, producing a signal embedded in sediments that might be recognized millions of years later. Even radioactive isotopes with long half-lives could survive as markers, providing a kind of cosmic timestamp of technological activity. Yet even with these clues, interpretation is difficult. The Earth is a complex system where natural processes often produce patterns that mimic those of intelligence. Massive volcanic eruptions release gases and metals in ways that can resemble industrial pollution. Meteor impacts redistribute rare elements across continents. Sudden climate shifts can change chemical ratios in ways that resemble the effects of burning fossil fuels. Distinguishing between natural phenomena and the fingerprints of a lost civilization is a subtle and ongoing scientific challenge. The thought experiment becomes even more fascinating when we imagine what a previous civilization might have done to survive in a world without modern energy sources. They would have needed to harness external energy on a large scale. Perhaps mining ores, building transportation networks, or altering the environment to sustain agriculture. Each of these activities leaves traces, but they are subject to the same forces of decay, recycling and erosion that have erased countless other aspects of Earth's history. Detecting these faint signals requires a careful combination of geology, chemistry, paleontology, and even astrobiology. In considering these challenges, the Silurian Hypothesis does not claim that previous civilizations existed. It simply proposes that the possibility is scientifically plausible, and that, if they did, their traces could be hidden, subtle, and easily misinterpreted as natural events. It asks us to expand our thinking, to look for anomalies in the record that might otherwise be overlooked, and to consider that Earth's memory is vast but imperfect. The process of searching for ancient civilizations is like reading a book where pages are missing, ink has faded, and entire chapters have been rewritten by time. It demands patience and a willingness to consider evidence that is both incomplete and ambiguous. It also reminds us of the fragility of our own existence, of how even the most advanced technology might leave only the faintest trace after millions of years. Ultimately, the challenge of detection is both scientific and philosophical. It forces us to confront the limits of what we can know about the past, and to acknowledge that the Earth may have witnessed stories we will never fully understand. The faint chemical signatures, the unusual isotopes, the anomalies buried deep in sedimentary layers, all of these hint at the possibility of something extraordinary. Whether or not previous civilizations existed, the exercise of searching for them deepens our appreciation for the fragility and resilience of life, intelligence, and the planetary story that stretches across incomprehensible spans of time. Chapter 7. Looking outward to understand what's hidden within. When we search for life beyond Earth, we're in many ways searching for a mirror, a way to understand our own planet's history through the lens of possibility. Astrobiology, the scientific study of life in the universe, asks profound questions. Under what conditions can life arise, evolve, and perhaps even develop intelligence? And if we look carefully at the patterns of life and extinction on other worlds, we may gain insights into what has happened right here, beneath our feet, on Earth. Consider Mars, a world that may have once harboured rivers, lakes, and a thin atmosphere capable of supporting life. Scientists study ancient Martian rocks, looking for chemical traces that might indicate microbial activity. Tiny changes in carbon isotopes, unusual mineral formations, or the presence of certain organic compounds could suggest that life once thrived there. Yet these signs, if they exist, are subtle, fragmented, and easily obscured by eons of erosion, radiation, and chemical alteration. Detecting them is challenging, requiring careful analysis, patience, and the right perspective. Now imagine applying that same perspective to Earth. If a civilization arose millions of years before humans, the challenges to detecting its existence are strikingly similar to the challenges we face in searching for life on Mars. Layers of sediment have been compressed into stone, tectonic activity has shifted continents, and chemical signals have been altered or diffused. The same principles of survival and decay that complicate the search for extraterrestrial life also apply to understanding our own ancient history. The comparison becomes a bridge, linking the distant stars to the hidden possibilities in our own soil. The search for extraterrestrial intelligence often focuses on technological signatures, signals, radio waves, or megastructures that might indicate an advanced civilization. These signals are analogous to the traces we might seek from previous civilizations on Earth. Just as we expect alien technology to leave detectable markers, we can imagine that prior industrial activity on Earth, if it existed, would leave chemical or isotopic fingerprints, subtle rearrangements of metals, or alterations in sediment patterns that could survive the test of millions of years. Interestingly, the rarity of industrial civilizations becomes a shared concern. Humans are the only example of an intelligent species capable of global-scale energy manipulation, at least that we know of. Even on a planet teeming with life for hundreds of millions of years, the rise of technological intelligence may be fleeting, brief enough that traces can vanish almost completely. In this sense, searching for past civilizations on Earth is not unlike searching for life in distant exoplanets. It requires careful inference from limited and subtle evidence. The parallels extend further. Just as astrobiologists study extremophiles, organisms that survive in volcanic vents, acidic lakes, or frozen deserts, we can imagine that ancient civilizations may have adapted to environments drastically different from those we inhabit today. Rising seas, shifting continents, or global climate upheavals could have forced societies to innovate or perish, leaving behind only chemical whispers in rock layers. Recognizing these traces requires a mindset that embraces subtlety, that considers indirect evidence as potentially meaningful, and that is willing to explore possibilities beyond the immediately visible. Looking outward also encourages humility. The universe is vast, and life is likely to be diverse in ways we cannot yet imagine. The absence of visible signals does not guarantee absence of presence. Similarly, the absence of architectural ruins or fossils from ancient civilizations on Earth does not necessarily imply they never existed. Their story may be hidden, encoded in subtle chemical shifts, isotopic anomalies, or irregularities in the sedimentary record. The universe teaches us that evidence can be fleeting, that time can erase even the most remarkable achievements, and that curiosity must extend beyond what is obvious. In this quiet reflection, we begin to see a pattern. The methods we use to search for life elsewhere can guide us in examining our own planet's deep history. Chemical fingerprints, isotopic anomalies, and abrupt environmental shifts are clues that may indicate intelligence, whether from another world or from an earlier Earth. By thinking across time and space, we expand our capacity to recognize the subtle traces of possibility, to read the silent stories etched into stone, and to imagine that the Earth may have hosted more than one intelligent civilization in its vast patient memory. This perspective does not provide certainty. It does not claim that previous civilizations existed, but it opens a door to curiosity, inviting us to consider what might have been, to interpret anomalies with an open mind, and to explore Earth's history not just as a series of natural events, but as a narrative that could include intelligence before humanity. In this way, looking outward allows us to look inward, examining our planet with new eyes, new questions, and a renewed sense of wonder. Chapter 8. How brief civilizations leave lasting marks. Civilizations, even the most advanced, are inherently fragile. History shows us that societies can rise and fall within centuries, sometimes leaving behind monumental structures, written records, or cultural artifacts, while others vanish almost completely, leaving barely a trace. When we consider civilizations that may have existed millions of years ago, the question becomes even more delicate. What, if anything, could survive the passage of such immense spans of time? Even in the best conditions, human constructions decay. Buildings crumble, metals corrode, plastics degrade. Our cities, impressive though they are, may vanish entirely over just a few 100,000 years under the forces of erosion, earthquakes, and shifting landscapes. Roads and canals will be smoothed over by wind and water, while underground structures may be crushed or submerged by tectonic activity. If this is true for humanity, then a civilization that existed millions of years ago would have left behind almost nothing recognizable to the naked eye. What does survive, however, is subtler and often chemical in nature. The legacy of energy use, industrial activity, and material manipulation leaves marks in the rocks and sediments of the Earth. Isotopic ratios in carbon, nitrogen, or oxygen may shift, reflecting massive releases of greenhouse gases or changes in agriculture and industry. Rare metals, redistributed by mining or manufacturing, can persist in unusual concentrations in sedimentary layers. Microplastics, synthetic polymers, and even long-lived radioactive isotopes act as durable, invisible signatures of industrial activity, capable of enduring millions of years under the right conditions. The brevity of a civilization is a critical factor. A society that thrives for only a few centuries may produce relatively weak geological fingerprints, compared to a civilization that lasts for tens of thousands of years. The longer the civilization's duration, the greater the likelihood that some markers will accumulate to detectable levels. Yet, even a brief civilization can leave clues if its activity is intense enough, or affects planetary systems on a large scale. Massive deforestation, extensive mining, or widespread chemical pollution could embed signatures in sediments that persist far beyond the collapse of society. The concept of fleeting civilizations also reshapes how we interpret anomalies in the geological record. Sudden spikes in carbon or isotopic ratios, abrupt environmental changes, and localized concentrations of unusual metals could all represent short-lived but impactful industrial activity. In many cases, these signals are subtle and easily attributed to natural causes, but the possibility remains that they may reflect the actions of intelligent species that rose and fell long before humans. Even the timing of extinction events intersect with this idea. Civilizations that existed during or just before mass extinctions would face extraordinary challenges. The catastrophic environmental changes could obliterate cities, infrastructure, and populations, leaving behind only traces too faint for ordinary detection. This may explain why the fossil and sedimentary records show abrupt changes in life and chemistry without any obvious signs of civilization. The very processes that end life also erase the evidence of intelligence. One must also consider the effects of spatial distribution. Civilizations confined to small continents, isolated regions, or marginal environments may leave extremely localized traces. Tectonic shifts and ocean formation over millions of years could further obscure these remnants, dispersing or burying them in ways that make detection exceedingly difficult. Large, widespread civilizations would have a greater chance of leaving detectable signatures, but even then the signs could be subtle, interpreted as natural anomalies unless carefully analysed with modern scientific methods. Reflecting on the brevity of civilizations also brings perspective to humanity's own presence. Our industrial society is a mere blink on the geological timescale, yet we've already altered the planet in ways detectable from orbit and measurable in sediments. It is possible that other civilizations, no matter how advanced, may have achieved similar feats, but left even fainter traces due to shorter durations, smaller populations, or more localized activity. The Earth's memory is selective, and time is an unforgiving editor. In contemplating fleeting empires, we learn to read the geological record with humility. The absence of obvious ruins does not confirm absence of intelligence. It may simply reflect the ephemeral nature of civilizations under the immense pressures of geological and environmental change. By focusing on subtle markers, chemical shifts, isotopic ratios, unusual metal deposits, we open a window into the possibility that intelligence may have appeared, transformed the world briefly and disappeared entirely, leaving behind only faint, almost ghostly traces in stone and sediment. Chapter 9. Time, Climate, and the Erasure of Memory. Earth's history is a story written in stone, but it's also a story continuously edited by the forces of climate and time. The planet is never still. Continents drift slowly across the globe. Oceans expand and contract. Ice sheets grow and retreat, and the atmosphere itself shifts in composition over millions of years. These planetary cycles have a profound impact on what evidence survives and what is erased, shaping the memory of the Earth in ways both subtle and monumental. Climate is perhaps the most persistent editor of the geological record. Ice ages advance across continents, grinding mountains and forests into sediment and redistributing soils. Rising and falling seas create new coastlines, submerge old ones, and deposit layers of sand, clay, and organic material that can obscure older traces. In periods of intense heat, chemical weathering alters rocks, dissolves minerals, and can even break down remnants of human or pre-human activity. A civilization, no matter how advanced, is fragile in the face of these relentless environmental processes. Over millions of years, even entire cities could be reduced to nothing more than faint chemical signals buried deep beneath sediments. Yet climate can also preserve. In exceptional circumstances, rapid burial by sediments during floods, volcanic ash falls, or landslides can entomb artifacts and organisms, protecting them from erosion for tens of millions of years. Ice cores, deep ocean sediments, and compacted peat can capture chemical and biological evidence that survives the passage of geological time. These moments of preservation are rare and often localized, but they provide the only glimpses into the otherwise vanished chapters of Earth's past. Planetary cycles operate on scales that dwarf human lifespans. Milankovitch cycles, which describe variations in Earth's orbit, tilt and wobble, influence glacial and interglacial periods, altering climate systematically over tens of thousands of years. Plate tectonics rearranges continents over millions of years, creating mountains, submerging land, and reshaping oceans. Volcanic activity can cover vast regions in lava and ash, sometimes preserving the record beneath while simultaneously erasing the landscape above. All of these cycles interact in complex ways, making the survival of evidence from any civilization inherently uncertain. The concept of time itself becomes almost surreal when we consider the scale. Millions of years are not just long, they're almost incomprehensible. Human civilization has existed for only a fraction of this span. Even the rise of complex life on land, which began around 400 million years ago, is dwarfed by the geological processes that can erase it. In this context, it is easy to see how a civilization could flourish, innovate, and disappear entirely, leaving behind no obvious physical remains, only subtle chemical hints in rocks, sediments, and isotopic ratios. Mass extinction events add another layer of complexity. When sudden climate changes cause massive die-offs, entire ecosystems vanish, and with them, the environmental conditions that might have preserved evidence of intelligence. Floods, volcanic eruptions, and wildfires associated with these events can obliterate structures, disperse materials, and alter chemical compositions. Even if a civilization had been widespread and technologically advanced, a single global catastrophe could erase most traces of its existence, leaving only the faintest geological signatures for those far in the future to ponder. Considering these interactions, we begin to appreciate the delicate balance required for evidence to survive. A civilization must exist for long enough to leave marks, it must impact its environment significantly, and it must coincide with periods of geological stability or rapid preservation. Any misalignment with these conditions could result in a civilization being erased almost entirely, as though it had never existed. This is one reason why Earth's deep history contains such enormous gaps, and why anomalies in the fossil record are so intriguing. They may represent moments where subtle traces survived against the overwhelming forces of time and climate. As we reflect on these forces, a pattern emerges. The erasure of memory is not absolute, nor is it random. It is a complex interplay of environmental pressures, planetary cycles, and the brevity of civilization itself. The Earth remembers in whispers, chemical shifts in rocks, isotopic anomalies, unusual deposits of rare metals, or abrupt changes in sediment composition. Each of these is a potential echo of what came before, a faint trace of life, intelligence, and activity that survived where so much else has vanished. By understanding how climate and time shape the preservation of evidence, we gain insight not only into our search for past civilizations, but also into the fragile nature of our own legacy. The forces that have erased the footprints of hypothetical ancient civilizations are the same that will eventually erase the traces of humanity. Our cities, roads, and monuments may crumble, but the subtle chemical imprints of our industrial activity, the legacy of the Anthropocene, may persist, detectable only to those who know how to look with patience, precision, and imagination. Chapter 10: The Science of Searching for Forgotten Worlds. Exploring the possibility of ancient civilizations on Earth is not merely a flight of imagination. It is a scientific endeavor rooted in careful observation, measurement, and reasoning. Scientists have developed a range of tools and methods to probe the deep past, allowing them to detect faint traces of activity long buried beneath the planet's surface. These methods combine geology, chemistry, paleontology, and even principles from astrophysics, creating a multidisciplinary approach to uncovering what may be hidden in time. One of the primary tools is isotope analysis. Isotopes are variants of elements that differ in their number of neutrons, and they carry subtle information about the environment in which they were deposited. For instance, a shift in carbon isotopes in sediments can indicate a sudden increase in carbon dioxide, potentially signaling large-scale burning of fossil fuels. Similarly, anomalies in nitrogen, oxygen, or sulfur isotopes can reveal changes in agriculture, industrial processes, or pollution. By carefully measuring these isotopic ratios in rock layers spanning millions of years, scientists can identify moments when the Earth experienced unusual chemical activity that might be linked to intelligent intervention. Chemical fingerprinting complements isotopic analysis. Certain elements or compounds, such as rare metals, synthetic materials, or long-lived radioactive isotopes, are almost exclusively associated with industrial activity. Their presence in geological layers where they should not naturally occur can act as a clue, a marker that something extraordinary may have happened. Even tiny concentrations, if widespread, can be significant, providing a map of ancient processes that altered the Earth on a local or global scale. Paleontology also plays a critical role. Fossil records reveal not only life itself, but also environmental conditions that shaped it. Sudden die-offs, unusual fossil distributions, or species that appear or vanish abruptly can indicate environmental disruptions. When combined with chemical evidence, these biological anomalies can suggest that the planet experienced unusual stress, possibly linked to intelligent activity. For example, mass extinction events that coincide with abrupt isotopic or chemical shifts may warrant a closer look, raising questions about causes beyond the purely natural. Advanced imaging and sediment analysis further enhance our ability to detect anomalies. High-resolution scanning of rock cores can reveal minute structures, layering patterns or microfossils that might otherwise go unnoticed. Magnetic resonance techniques can detect subtle mineralogical changes, while spectroscopy can identify unusual chemical compounds embedded deep in sediments. Each tool allows scientists to peer into the past with increasing precision, uncovering details that could hint at the presence of lost civilizations. Another avenue of investigation is comparative analysis with known industrial impacts. By studying the fingerprints of human activity today, the isotopic shifts, the accumulation of plastics and metals, the global distribution of pollutants, scientists create a reference model for what an industrial civilization looks like in the geological record. This model then serves as a lens to examine ancient sediments, helping distinguish between natural anomalies and those that might reflect intelligent intervention. It is a delicate process, requiring both rigor and imagination, balancing skepticism with openness to extraordinary possibilities. Computational models also assist in this search. By simulating how sediments, metals, and chemical compounds move through the Earth over millions of years, researchers can predict how evidence of a civilization might survive or be erased over geological timescales. These models help narrow the search, suggesting which regions, layers, or chemical markers are most likely to retain traces of ancient industrial activity. The models also illustrate the limits of detection, reminding us that the absence of evidence is not necessarily evidence of absence. Finally, the search for ancient civilizations requires interdisciplinary collaboration. Geologists, chemists, paleontologists, archaeologists, and even astrophysicists must combine their knowledge to interpret subtle signals accurately. Each anomaly must be carefully evaluated, considering natural processes that could mimic the fingerprints of intelligence. The work demands patience, meticulous observation, and a willingness to question assumptions while remaining grounded in empirical evidence. Through these methods, scientists transform Earth itself into a library of hidden stories. Rock layers, sediments, isotopes, and fossils become pages in a narrative that stretches across hundreds of millions of years. While we may never uncover definitive proof of ancient civilizations, the tools at our disposal allow us to explore the possibility with rigor and curiosity. Every chemical anomaly, every isotopic shift, and every unusual fossil becomes a whisper from the past, inviting us to consider that Earth's history may be richer, stranger, and more complex than we have ever imagined. Chapter 11. Geological Clues That Make Us Pause. There are moments in Earth's deep archive when the rock seems to cough up a line we do not fully understand. An abrupt chemical spike, a strange concentration of metals, a thin layer that splits one world from the next. These are the case studies that draw scientists' attention and spark quiet wonder. In this chapter, we move slowly through several of the most intriguing anomalies in the geological record, listening carefully to what each one might be saying, and remembering always to balance curiosity with caution. One of the first places scientists look when they think about hidden, large-scale disturbances is the modern framing of the problem itself, the Silurian Hypothesis. This is not a claim that a prior industrial civilization definitely existed, but a structured way of asking what signals such a civilization would leave and whether those signals could survive for millions of years. The work of Gavin Schmidt and Adam Frank gently reframes the question. By examining the lasting chemical and sedimentary fingerprints of our own industrial age, we can build a template for what to search for in older strata. The Silurian Hypothesis gives us both a checklist and a cautionary note. Some signals are distinctive, others can be remarkably good mimics of natural events. One of the clearest, most studied ancient anomalies is the Paleocene-Eocene thermal maximum, or PETM. About 56 million years ago, the planet warmed very quickly, in geological terms, accompanied by a large negative carbon isotope excursion that indicates an injection of light carbon into the atmosphere and ocean system. The scale and speed of that carbon release looks strikingly like what modern, industrial carbon emissions do, which is why the PETM often features in discussions about detectability of ancient technological impacts. Scientists continue to debate the cause, massive volcanic emissions, methane release from ocean clathrates, or other natural processes, but the PETM remains a textbook example of how a geochemical signature can point to a planet-scale disturbance long before humans. Another signature that people immediately recognize is the iridium-rich layer at the Cretaceous-Paleogene boundary. This thin global stratum marks the asteroid impact that is widely accepted to have precipitated the mass extinction that ended the age of dinosaurs. Here the evidence is relatively unambiguous. an extraterrestrial source of rare metals and impact spherules, combined with shocked minerals and a global pattern of devastation. The clarity of the KPG boundary shows us two things. First, certain catastrophic events leave unmistakable, globally correlatable fingerprints. Second, those same events can bury or obliterate any complex structures that existed immediately prior, making it easy for an advanced society, if one had existed, to be hidden beneath the impact's blanket. Spherules and microscopic metallic beads turn up in many layers of the rock record, and they are part of the interpretive challenge. Impact events and large eruptions commonly produce glassy or metallic spherules, microtectites and impact spherules, formed when rock is vaporized and recondensed in a molten plume. These tiny, often glassy spheres are a natural product of hypervelocity impact and can be widely dispersed, producing layers that look, at first glance, like manufactured artifacts. Distinguishing between anthropogenic spheres, modern industrial pollution, or combustion residues and impact-produced spheres requires careful morphological and chemical analysis. The presence of spherules alone is not a smoking gun for intelligence. In short, nature also makes beads. Moving to a more modern but geologically durable signal, plastics and plastiglomerates. Anthropogenic materials like plastics are abundant today and are already being incorporated into sediments in beaches, estuaries, and deep-sea deposits. Researchers have documented composite rocks that include molten plastic fused with natural rock fragments, called plastiglomerates, which could serve as a very unusual and diagnostic marker for the Anthropocene horizon in future strata. If we accept that synthetic polymers are novel and durable on geologic timescales under certain conditions, then their presence acts as a clear and so far uniquely human signature, one that would be hard to explain by natural processes and that future geologists could, in principle, find and recognize. These case studies teach a few steady lessons. First, many of the most striking anomalies in Earth's record have plausible natural explanations. Impacts, volcanism, methane releases, and tectonic rearrangements can all reshape chemistry and bury or destroy evidence. Second, certain classes of evidence, distinctive isotopic shifts, long-lived radionuclides, synthetic polymers, or concentrations of processed metals in contexts where geology would not place them naturally, would be the most convincing signs of industrial activity, and thus are the highest priority targets for investigation. Third, the absence of unambiguous manufactured artifacts in deep time does not falsify the possibility of earlier intelligence. It simply underscores how effective geological processes are at erasing fragile structures. When we examine the record with this balanced frame, curiosity grounded in method, we begin to see why the question is not closed. There are events like the PEPM that look alarmingly similar to modern industrial impacts on climate, and there are physical markers like plastics that would be nearly impossible to replicate by natural processes alone. But there are also many ways natural Earth systems can imitate or obscure technological signals, and so extraordinary claims require extraordinary evidence. Isotopic signatures paired with anomalous mineral distributions and a lack of plausible natural causal chains would be the kind of converging evidence scientists would demand. We end this chapter with a quiet reminder. Case studies give us both optimism and restraint. They point to the methods we should use: careful geochemical forensics, high-resolution stratigraphy, and interdisciplinary comparison, and they teach humility about what time can remove. The rock preserves hints, not always answers. It offers puzzles that reward patient listening. If anything, the anomalies we've described are invitations to look more closely, to drill deeper, to measure with finer instruments, and to hold our conclusions gently, knowing that Earth's slow memory keeps both secrets and signs. Chapter 12. The best places and methods to find ancient signals. When we decide to search for the faintest echoes of forgotten civilizations, the question becomes both practical and poetic. Where on Earth might the planet have kept secrets, and how do we listen without disturbing the delicate pages of time? Imagine the Earth as an immense library with many rooms. Some rooms are dry, well organized, and filled with pages we can read easily. Others are damp, folded, burned, or scattered across the floor. Our job as careful readers is to find the rooms most likely to have preserved a line or two of text, and to bring the gentlest touch to turning those pages. The first places to visit are those where deposition has been steady and burial rapid, where sediments accumulate without being repeatedly ground into new rock. Deep ocean basins that receive steady rain of microscopic shells and dust, quiet lake beds that trap fine mud for millions of years, and sheltered estuaries where organic material is rapidly buried. These kinds of environments act like soft envelopes, sealing chemical and biological signals before they can be scattered by storms or scavenged by tides. In these settings, fine-grained sediments build up slowly but continuously, creating a layered history that preserves subtle changes in chemistry and microfossil life. A long, unbroken core pulled from such a bed becomes a chronicle, and scientists can read it like a slow-motion movie of climate, chemistry, and life. Equally promising are ancient continental basins and cratonic interiors, the stable heartlands of continents where tectonic upheaval has been minimal for very long periods. In these regions, sequences of sedimentary rock can remain relatively undisturbed for hundreds of millions of years. Buried soils or paleosols that formed on ancient land surfaces sometimes survive as pockets of preserved chemistry and microstructures, and they can contain traces of atmospheric composition, plant life, and the interaction of organisms with their soils. Coal seams and peat layers, formed from dense vegetation and often buried rapidly, can hold chemical evidence of atmospheric and biological activity that would be hard to erase entirely. Places that record major transitions, cliffs and outcrops that cut across boundaries between geological epochs, are particularly important. These stratigraphic sections that span abrupt events, such as warming spikes or extinction horizons, act like bookmarks in the planet's story. Coring into or sampling across those horizons with high-resolution techniques allows scientists to watch, layer by layer, how chemistry and life shifted. The sections that preserve the Paleocene-Eocene boundary, for example, are among the locations that geoscientists study most intensively for abrupt carbon changes. In practical terms, researchers seek sites with continuous sedimentation, minimal later disturbance, and good exposure or accessibility for coring. Under the seas, the deep abyssal plains and certain anoxic basins are also excellent archives. Anoxic conditions, that is, waters low in oxygen, suppress biological decomposition and so preserve organic molecules and delicate structures that would otherwise be destroyed. Sediments in these areas can capture long-term chemical trends and preserve organic compounds, microorganisms, and tiny particles that could be signatures of past activity. Submarine fans and continental slope deposits, where sedimentation rates can be high, are additional targets because rapid burial increases the chance that transient signals are captured before they dissipate. Beyond the natural depositional environments, we use tools that let us see what is hidden beneath the surface without disturbing it recklessly. Aerial and satellite imagery reveals gentle anomalies in landforms and vegetation that betray buried structures or sediment patterns. LIDAR, light detection and ranging, can peel away forest canopies to show subtle terraces, buried river channels, and ancient shoreline features. ground-based geophysics, magnetometry to detect metal anomalies, ground-penetrating radar to reveal shallow buried layers, and seismic reflection to image deeper stratigraphy, gives us maps of what lies below so that coring and trenching target the most promising zones. These remote and non-invasive surveys are like listening to the hum of an old instrument before deciding where to place a microphone. When it is time to take a sample, the methods are careful and deliberate. Scientists extract long sediment cores from lakes and the seafloor, working slowly to preserve the order of layers. Contamination is the enemy. Each sample is handled with clean tools, sealed immediately, and logged with meticulous detail so that tiny chemical differences are not confused with modern pollution. On land, trenching into exposed sequences and drilling boreholes into soft, ancient sediments allow researchers to sample paleosols, coal seams, and other deposits that may contain preserved organic molecules, microplastics, trace metals, or unusual isotopic ratios. In many cases, the greatest value comes from high-resolution sampling, taking slices of sediment centimeters thick or finer so that changes over decades or centuries can be resolved in the geological record. Back in the laboratory, a suite of complementary analyses becomes the interpreter's toolkit. Isotope geochemistry reads the subtle ratios of carbon, nitrogen, oxygen, and other elements to reveal shifts in atmospheric composition or biosphere function. Trace metal measurements and ultrasensitive detection of synthetic compounds can identify materials unlikely to be produced purely by natural processes. Organic geochemistry, using techniques like gas chromatography and mass spectrometry, can hunt for specific molecules, remnants of complex chemistry that might hint at biological or industrial processes. Imaging methods, from scanning electron microscopes to X-ray fluorescence, reveal microscopic structures and elemental maps. Every technique provides a piece of the puzzle. Only by combining them can we approach the truth with confidence. Crucially, the most convincing discoveries arise from a multi-proxy approach. When independent lines of evidence converge, a carbon isotope shift accompanied by a change in pollen assemblages, a sudden disappearance of sensitive microfossils, unusual trace metal concentrations, and the presence of synthetic-like compounds in the same stratigraphic slice. Together, these patterns form a chorus rather than a single voice. Field campaigns are therefore designed with redundancy and replication in mind. Multiple cores from different locations, blind control samples to rule out contamination, and repeated analyses to confirm that results are real and ancient, not modern intrusions. Finally, the search is patient and global. No single site can answer the question alone. We map patterns across continents and oceans, comparing coeval layers to see if an anomaly is local or planetary in scale. We favour regions where burial was rapid and tectonic recycling minimal, where organic preservation was high, and where stratigraphic continuity is best. We remember that even when a promising signal is found, alternative, natural explanations must be carefully considered and ruled out. The goal is not to prove a dramatic hypothesis quickly, but to build a careful, reproducible dataset that speaks clearly across disciplines. In this gentle pursuit, the planet teaches us humility. The best places to listen are those that have managed to keep their pages intact. Quiet basins, anoxic depths, stable continental interiors, and horizons that span major transitions. The best methods are those that preserve context, avoid contamination, and combine many lines of evidence. When we work slowly, respectfully, and with breadth of vision, the Earth gradually reveals its secrets, sometimes whispering of only natural processes, sometimes offering mysteries that do not yet have an ordinary explanation. Whether we find clear signs of past intelligence or simply deepen our understanding of the planet's natural rhythms the journey itself is a lesson in patience, care, and wonder. Chapter 13. False Positives and the Discipline of Doubt. When we listen for whispers from lost civilizations, we must also learn to listen for echoes that are not voices at all, but tricks of geology and chemistry. Earth is an imaginative storyteller. It produces patterns that look meaningful, repeating motifs that can easily be mistaken for signs of intelligence if we aren't careful. In this chapter, we slow our pace and practice scientific caution, exploring how natural processes can mimic technological signatures, why skepticism is essential, and how researchers separate ordinary geology from truly extraordinary claims. Many of the phenomena that attract attention have perfectly ordinary origins. Tiny glassy beads in sediments, for example, can resemble manufactured spherules, but they are also the natural offspring of violent events. Meteor impacts and powerful volcanic eruptions splash molten droplets that cool into spherical forms and rain down across continents. Hydrothermal vents on the seafloor create metallic precipitates that can concentrate rare elements in ways that, at first glance, seem unusual. High-temperature fumaroles and black smoker systems precipitate metals, grow mineral chimneys, and create textures that could be misread as the residue of smelting or ore processing, unless their morphology and geologic context are carefully examined. Isotopic anomalies are similarly beguiling. A sudden shift in carbon isotopes in a sediment layer may look like the signature of massive fossil fuel burning, yet methane released from destabilized hydrates, large volcanic carbon emissions, or even prolific organic carbon burial can produce comparable Delta 13C excursions. Shifts in nitrogen isotopes might hint at industrial fertilizer use, but they are also produced by changes in marine productivity, large-scale denitrification during anoxia, or biological innovation. This is not deception, but complexity. Earth's biogeochemical cycles produce large, abrupt changes that are entirely natural and from a broad vantage can eerily resemble the fingerprints of an industrial world. There are also striking natural examples that remind us how easily we could be misled. Some ore-forming processes concentrate metals in ways that produce exceptionally high local enrichments. Hydrothermal circulation near mid-ocean ridges or ancient volcanic arcs can deposit copper, platinum group elements, and other metals into narrow horizons that, if sampled in isolation, might look anomalous relative to surrounding geology. Natural nuclear reactions have occurred too. Places like the natural reactors at Oklo in Africa show that under particular conditions, uranium deposits can undergo self-sustaining fission and leave behind unusual isotopic signatures. These natural reactors provide a powerful lesson. Certain isotopic patterns once thought to indicate technological processes can, in fact, have perfectly natural explanations when geology assembles the right conditions. Diagenesis, the suite of chemical changes that occurs in sediments after they are deposited, adds another layer of subtlety. Molecules produced at the surface can be transformed by microbial communities, altered by changing redox conditions, or recrystallized into new mineral forms as pressure and temperature rise. Polymers and organics may break down and reconstitute into forms that look exotic, but are simply products of deep chemical reworking. Even microplastics, which are promising Anthropocene markers today, can be physically and chemically altered in ways that make them hard to distinguish from certain naturally occurring organic residues once they have been buried and chemically modified for millions of years. The lesson here is not pessimism, but prudence. Extraordinary claims require convergence. A single odd result, a bead, a shifted isotope, an unusual concentration, rarely suffices to overturn well-established explanations. Instead, scientists look for multiple lines of evidence that intersect in time and space. Consistent isotopic shifts accompanied by organic molecules that are hard to produce naturally, unusual trace metal distributions found across many unrelated basins, long-lived radionuclides with decay signatures incompatible with known natural processes, and sedimentary patterns that show rapid, globally coherent changes rather than local quirks. When these independent proxies tell the same story, the case becomes stronger. When they do not, caution is warranted. Context matters deeply. A metal-rich layer found in a place dominated by hydrothermal activity should be read differently from a similar layer discovered in a quiet, stable continental basin. A Delta 13C excursion coincident with widespread ash layers and known volcanic episodes will usually be pinned to igneous activity. The same excursion without volcanic markers, but with unusual organochlorine compounds or synthetic-looking polymers, would be more puzzling and require intensive follow-up. Spatial distribution is a key test. Natural events often leave geographically coherent patterns tied to tectonic or volcanic provinces, while a truly global, synchronous signal distributed across disparate depositional settings would be more suggestive of a planet-scale cause. Good science also anticipates contamination and modern intrusion. Modern pollutants can move through soils, groundwater and sediments, masquerading as ancient signals if cores or outcrops are not carefully dated and handled. Rigorous sampling protocols, clean sampling, multiple replicate cores, independent labs, and cross-dating with biostratigraphy or radiometric methods are essential for ruling out modern contamination. The discipline of doubt includes these procedural safeguards, not leaping to a sensational interpretation until every mundane explanation has been eliminated. Finally, humility is the scientist's best companion. The absence of unambiguous artifacts in deep time does not prove a negative. It only reminds us of the limits imposed by time and process. At the same time, the history of science shows that extraordinary ideas must survive extraordinary attempts at refutation. If the search for past civilizations is to be productive, it must be built on meticulous fieldwork, conservative inference, and the willingness to be wrong. We must be comfortable living with uncertainty while gradually accumulating evidence that either tightens the noose around a hypothesis or gently releases it. In the end, the discipline of doubt is not a rejection of wonder, but its careful steward. It protects us from reading meaning when none exists, while leaving room to pursue genuine anomalies with the respect they deserve. As we move forward in this exploration, we will carry both curiosity and skepticism, twin lamps that light the path through deep time, helping us distinguish nature's illusions from the rare, luminous traces that might truly be the echoes of other minds. Chapter 14. Evidence that could suggest we are not the first. As we sit quietly with this question, it helps to arrange the evidence into careful categories, the kinds of things scientists would look for if they wanted to know whether intelligence had left a trace before us. None of these items by itself proves anything extraordinary. Taken together and interpreted with rigour, they form the threads of a hypothesis worth exploring. What follows is an extended, gentle tour through the strongest, most interesting pieces of evidence, and why each one makes the question feel less impossible and more scientifically approachable. First, there are abrupt planet-scale chemical events recorded in sediments that look surprisingly similar to what we would expect from rapid industrial perturbations. The Paleocene-Eocene thermal maximum, a warming spike around 56 million years ago, is the clearest example. A large, sudden injection of isotopically light carbon into the atmosphere and oceans, rapid global warming, acidification of the seas, and major biotic turnover. When scientists look at the isotope record, The speed and magnitude of the PEM's carbon shift resemble the fingerprint of a massive release of stored organic carbon, the kind of signal modern industry produces by burning fossil fuels. That resemblance does not prove industrial activity then, but it does mean the geological record contains episodes that, chemically and dynamically, are not unlike the changes we cause today. Second, the rock record contains unusual layers and particles whose origins are sometimes ambiguous. Tiny spherical particles, or spherules and microtectites, are commonly produced by catastrophic natural events like meteor impacts and large explosive eruptions. They're also produced by high-temperature anthropogenic processes such as smelting or combustion. Careful morphological and chemical study can distinguish many natural from modern industrial spherules, but the existence of spherules in very old strata reminds us that spherical high-temperature droplets are not an unambiguous signature of intelligence. In short, nature already makes some of the things we might naively expect only industry could make, so scientists must rely on detailed chemistry and context to tell the difference. Third, there are examples in Earth's history showing that processes we think of as technological can also have natural analogues. The natural nuclear reactors discovered at Oklo in Gabon are a striking case. Under the right geological conditions, uranium ores moderated by groundwater went critical nearly 2 billion years ago, producing fission products and isotopic anomalies that look, in some respects, like the fingerprints of human nuclear reactions. The Oklo reactors teach a cautionary lesson. Certain isotope patterns, even those associated with nuclear processes, can occur without intelligence when geology arranges the right ingredients. This means that the mere detection of odd radioisotope ratios in ancient rocks would not automatically imply a former civilization. The geological context must be understood first. Fourth, the Anthropocene itself provides an instructive template for what survives and what does not. Researchers have shown that long-lived markers of modern industry already exist, and that some of them are likely to be detectable far into the future. Plastics fused into rock-like composites, so-called plastiglomerates, persistent microplastic particles sinking into deep sediments, and distributions of rare metals altered by mining and industry are likely to become identifiable horizons in the stratigraphic record. If prior industrial activity took place in the distant past, similar classes of signals, synthetic polymers, processed metal concentrations, long-lived pollutants, would be the most convincing sorts of evidence to search for, precisely because they are durable and chemically distinctive. The presence of such materials in ancient, well-dated strata would be hard to explain by ordinary geological processes alone. Fifth, mass extinctions and catastrophic events both create opportunities for erasure and for preservation, a paradox that complicates the search. An asteroid or supervolcano can instantly erase cities, bury landscapes in ash, and make the physical traces of a civilization vanish, while at the same time creating a marker horizon, for example, the iridium-rich KPG boundary, that will be visible globally for millions of years. This means a civilization that existed immediately before a massive catastrophe could be both completely destroyed and effectively hidden beneath a clear geological event that future scientists would interpret as natural. That interplay between burial and obliteration helps explain why the fossil and artifact records can be silent, even if remarkable events once occurred. Sixth, there are biologically driven anomalies that give us pause. Rapid turnovers in species, sudden changes in pollen and plant assemblages, abrupt disappearances of sensitive microfossils, and episodes of ocean anoxia show that the biosphere has undergone sharp transitions at various times. Some of these transitions coincide with chemical excursions that remain difficult to explain completely by single natural causes. When biological change co-occurs with chemical anomalies, the combination becomes especially interesting. It is exactly the kind of multi-proxy signal that the Silurian hypothesis points to as being worth investigating further. But again, interesting is not the same as proven. Multiple plausible natural mechanisms remain for many of these cases, so the pattern is provocative more than decisive. Seventh, the geographic and temporal gaps in the record themselves are a form of suggestive evidence. Sedimentary preservation is patchy. Some environments accumulate and preserve sediments for tens of millions of years, while others are swept clean. If a civilization developed in a region that later subducted, eroded or sank beneath an ocean, its visible remains could be permanently lost. The absence of global continuous coverage in the strata means that entire chapters of planetary history may simply never have been recorded in the rock record accessible to us. This ignorance of absence invites cautious speculation. The planet may have been able to host industrial activity in places and times that left only very subtle chemical traces or none visible to traditional paleontology and archaeology. The point is methodological humility. The gaps create room for possibility, not proof. Eighth, we have to confront modern claims and sensational interpretations carefully. Popular accounts sometimes point to odd metallic spheres or anomalous objects and frame them as pre-human artifacts. Rigorous science demands independent replication, careful stratigraphic control, and full geochemical context before any extraordinary claim can be entertained. Many past anomalies once touted as inexplicable have later been resolved as products of impacts, volcanism, diagenetic alteration, or contamination. This historical pattern is why mainstream researchers emphasize conservative, repeatable tests rather than headline-catching assertions. Ninth, science offers a clear roadmap to test these possibilities. The Silurian hypothesis itself proposes the methods. Search for globally synchronous isotopic anomalies that are inconsistent with known volcanic or impact signatures. Look for long-lived radionuclides or alloy compositions that cannot be produced naturally under known conditions. Hunt for synthetic organic compounds or polymer residues embedded in ancient sediments, and demand correlation of multiple independent proxies across widely separated depositional settings. It is the convergence of independent lines of evidence, chemical, isotopic, mineralogical, and stratigraphic, that would begin to change a provocative possibility into a credible claim. Finally, and perhaps most gently, we must accept the provisional nature of this entire inquiry. The best current science says that while Earth's past contains puzzling, powerful events and curious anomalies, there is no confirmed, unambiguous evidence that an industrial civilization once existed before humans. At the same time, the question is scientifically meaningful because the kinds of signatures we would look for are in principle detectable, and because some ancient events display features that merit deeper, more careful investigation. This is how science proceeds, not by insisting on a foregone conclusion, but by setting up tests, gathering data, and allowing certainty to emerge, or to fade, with evidence. The balance of probabilities today leans toward natural explanations for the anomalies we know, but the door remains open to discovery if converging, reproducible signals are ever found. So when we gather all these threads together, PETM-style carbon spikes, ambiguous spherules, the example of natural reactors, durable synthetic markers like plastiglomerate, the burying power of global catastrophes, and the patchy coverage of the rock record, we find a landscape of informed wonder. Each strand, taken alone, is explainable by familiar Earth processes. Taken together and approached with rigorous methods, they become a careful scientific argument for why the question of earlier civilizations is not frivolous, but rather a legitimate and fascinating frontier of inquiry. We move forward not by abandoning skepticism, but by allowing curiosity and method to guide us into the silent chapters of deep time. Chapter 15. The anomalies that refuse to fade. When considering the question of whether humanity is the first civilization on Earth, it is easy to become lost in theory, in speculation, in what-ifs. But to keep our journey grounded, we must walk through the specific anomalies. Those fragments of evidence that seem, however faintly, to suggest that something unusual may have happened before us. Some are likely natural, some are surely misinterpreted. Yet together they build a gallery of curiosities too persistent to dismiss entirely. If there is any chance that advanced life came before, these are the shadows it may have left behind. One of the most discussed anomalies is the discovery of tiny metallic spheres embedded deep within geological layers that predate humanity by millions, even billions, of years. In mines of South Africa, at depths corresponding to strata around 3 billion years old, workers uncovered smooth, grooved metallic spheres, some made of materials not common in surrounding rock. Their symmetry is remarkable, some almost perfectly round, with grooves etched around their circumference. The scientific explanation is that they are natural concretions formed by slow, mineral growth in ancient sediments. But skeptics point out that their uniformity and markings are unusual enough to warrant deeper scrutiny. Even if natural, they remind us how easily we could mistake a genuine artifact for a geological oddity, or vice versa. Coal mines in North America have also revealed curious finds. Reports describe metal tools, imprints, and even what appeared to be a delicate gold chain encased in solid coal dating back tens of millions of years. Mainstream geology argues that coal seams form under pressure and can create cracks into which younger objects might intrude, giving the illusion of antiquity. Still, these stories persist in the literature of anomalies. If even one of them proved authentic, it would overturn everything we thought we knew about the history of technology on Earth. Then there are the footprints. Human-like impressions found in strata said to be far older than humans themselves. In the Paleocene River of Texas, for example, fossilized dinosaur tracks appear alongside what some claim are human footprints. Most scientists believe these supposed human tracks are either eroded dinosaur prints or natural formations resembling feet. Yet, they continue to attract attention, largely because they force us to ask, how secure is our understanding of the fossil record? If entire epochs can be misread, might we be missing more subtle signs of advanced beings? Beyond artifacts and imprints, there are the broader geological puzzles. Consider the Paleocene-Eocene thermal maximum, which we touched on earlier. A sudden and massive injection of carbon into the atmosphere, leading to rapid global warming. This event occurred about 56 million years ago and lasted less than 200,000 years, a blink in geological terms. Volcanic eruptions and methane release are plausible culprits, but the fingerprints also resemble what we humans are doing to the planet now. If a prior civilization had burned fossil fuels at a planetary scale, the isotopic signature it left behind would look very similar. Of course, the cautious scientific answer is that natural processes are more likely. But the overlap in effects keeps the question alive. Another anomaly is the presence of massive underground structures that challenge our sense of scale. In parts of South America and Siberia, researchers have discovered vast ancient tunnels carved through rock and clay, some large enough for humans to walk through comfortably. Mainstream interpretations suggest they are the work of giant prehistoric animals such as ground sloths or armadillo-like creatures. Yet their size, smoothness, and the sheer effort involved provoke curiosity. Could natural creatures alone have carved such enduring features, Or might we be glimpsing the remnants of something else entirely? Ancient myths also add weight to the possibility. Cultures separated by oceans and millennia often tell stories of advanced societies lost in cataclysms. Atlantis in Greek lore, the Great Flood in Mesopotamian tablets, and similar tales across Africa, Asia, and the Americas. While myths cannot be taken as direct evidence, they serve as cultural memory. They may encode real events, sea level rise at the end of the last ice age, tsunamis, or volcanic eruptions. But if those myths represent even fragments of truth about forgotten civilizations, then humanity may simply be one in a cycle of rise and collapse. We must also consider the principle of geological erasure. The Earth is not a static archive. Its surface is constantly recycled by tectonic activity. Entire continents have been swallowed, mountain ranges razed and worn away, seabeds lifted into the sky. If a civilization had existed more than a few million years ago, most of its surface works, cities, roads, monuments, would be erased. Only subtle chemical traces or rare preserved artifacts might endure. This explains why the absence of obvious ruins is not in itself evidence against the possibility of earlier civilizations. The lack of evidence may simply reflect the brutal efficiency of Earth's own geology. Even within our own relatively recent history, examples show how fragile civilizations are. Consider the Mayan cities swallowed by the jungle, forgotten for centuries until rediscovery, or the ruins of Göbekli Tepe, deliberately buried by its builders more than 10,000 years ago, only to be uncovered in our own era. If such advanced human achievements could be hidden for so long within the shallow layers of history, how much more might be hidden within the deep strata of geological time? When all these anomalies are placed together, metallic spheres, coal seam artifacts, footprints, unexplained carbon events, immense tunnels, global myths, and the erasing power of geology, they form a constellation of possibility. None of them, taken alone, is strong enough to prove that advanced civilizations existed before us. But together, they challenge us not to dismiss the idea too quickly. They remind us that Earth is old beyond comprehension, and that our short chapter may not be the first written upon its pages. The question then becomes not only whether there were civilizations before us, but whether traces of them could still be waiting to be recognized. If we approach the search with humility and openness, we might learn not only about others who came before, but also about the fragile impermanence of our own.